Hi again, everybody. Welcome to part two of the derivation of the randomly chosen positive integers being relatively prime. Somehow we have to get to 6 over pi squared. We left off here with this divisibility issue, and we're now moving into the realm of probability. So we concluded that a number is a randomly chosen integer is divisible by 2 with a probability of 1/2, and the same for a second number. And these are independent events, meaning m and n have nothing to do with each other. There's a technical definition for independent events, but we're not going to worry about that right now. From the nature of how m and n are selected, we consider these to be independent. Well, what if I ask the question, what is the probability of a compound event? Like 2 divides m and 2 divides n. In other words, what is the probability that m and n are both divisible by 2? Now, if that happens, then m and n would not be relatively prime. And we need this concept in order to arrive at our result. In the subject of probability, which you'll pick up in various courses in middle school and high school and further on in college, we have a formula for independent events. We take the probability of each separate event and multiply them together. And that should be logical. We saw some of the multiplication principle when we were counting in earlier videos. And does it make sense that m and n would both be even with a 25% probability? Well, remember, we could have odd, even. M could be odd, n could be even. I think I'll do that another way. We have 4 possibilities. They could both be odd. Excuse me. They could both be even. M could be odd. N could be even. We'll put m and n at the top. And finally, m could be even and n could be odd. And these 4 are equally likely, kind of like tossing 2 fair coins, heads, 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 tails, tails, heads, tails, tails. Each would occur with a 25% probability. So there is a 1/4 chance that m and n are both divisible by 2. I could develop that further. We don't have the time in this video. So we're going to move on and accept that the probability is 1 over 2 squared. Believe it or not, it's related to that. So we at least got a probability that is connected to this original series. We have a lot of machinery left we need to use to arrive at the final result, but we're starting. Let's look at 3 now. So for 3, what is the probability that 3 divides the randomly chosen integer m from 1 to 100? Well, there are 33 multiples of 3, 3, 6, 9, up to 99. So the probability from this set would be 33 over 100, 0.33, which is approximately 1/3. Not exactly. As we increase the set of integers to 1,000 integers or 1,000,000 integers, and we let the number of integers increase beyond all bound, heading toward infinity, we would find that this relative frequency, this probability, would become 0.333, 3333, and would in fact approach 1/3. So for our purposes, we're actually going to say that the probability is 1/3 when you're dealing with an infinite set. Not proving it, I'm asking you to accept that. Let's again do the compound event. What is the probability that 3 will divide m and 3 will divide n? This would be 1/3 times 1/3, which is 1/9, which is approximately 11%. Okay. So we are now beginning to get to probabilities that look like some of the terms of our original Euler conjecture, which he derived as pi squared over 6. Pretty amazing stuff. So this is the probability that m and n are both divisible by the same prime p. If this happens, then we know m and n are not relatively prime. Notice I keep focusing on not relatively prime. As it turns out, it's much easier to work with the not condition first, and then we'll move over to relatively prime. So let's go back to 2. We found out that the probability that m and n are both divisible by 2 was 1/4. Therefore, it follows that implies that the probability that m and n are not both divisible by 2 is the complementary probability, 3/4. And in other words, there's a 3 out of 4 chance that the two numbers you pick are not both even. We saw that. The two could both be odd. One could be odd, one could be even. The first could be even, the second could be odd. So there are 3 chances out of 4. This concept is extremely important, and that pretty much finishes our prerequisite knowledge for probability. Multiplication of probabilities, subtracting from one to find the opposite, or the complementary. Saying that m and n are not both divisible by 2 doesn't mean that m and n are relatively prime. It simply means they're not divisible by the same prime 2. So what we really need to get to is that m and n are not divisible by 2, and m and n are not both divisible by 3, and m and n are not divisible by the next prime 5, etc. Again, this is a compound event, and each of the events here are independent of each other. I'm not going to get into the details of that. But if you put all of these conditions together, then we can say that we're asking the question, what is the probability that m and n are not divisible by the same prime? If they're not divisible by 2, and they're not divisible by 3, and they're not divisible by 5, they're not divisible by 7, not divisible by the same prime p, then we're really asking the question, what is the probability that they are relatively prime? That's a huge concept here. I have 30 seconds left on this video, but I'll repeat it one more time. Saying that m and n are relatively prime means they're not divisible by the same prime p for any of the infinitely many primes. I've reduced it to these conditions, doing each separate prime. We're going to express in part 3 what the probability is. for each of these, and then we're going to continue from